In our previous analysis, we used phase plane mapping to outline the qualitative geometry of nonlinear systems. We plotted limit cycles, singular points, and basins of attraction. Numerical integration is highly effective for plotting these exact trajectories. However, a numerical solver operates as a parameter-blind black box. It computes the coordinates point by point without defining the overarching algebraic rules. This graph displays the time response of a van der Pol oscillator settling into a stable limit cycle. While the numerical output allows us to see exactly what the system does, the underlying parameters that dictate this specific shape remain hidden within the calculation. To actively design a physical system, like a nonlinear vibration absorber, we need exact mathematical relationships. We must know precisely how an adjustment to the input frequency dictates the final amplitude. The standard forced Duffing equation serves as our foundational model for these complex interactions, incorporating damping, linear stiffness, and a cubic nonlinear term. The core roadblock in this field is that exact closed-form solutions using elementary functions do not exist for this class of nonlinear ordinary differential equations. Numerical methods provide evidence for specific cases, but deriving general design rules for these systems requires a different set of approximate analytical techniques. We begin with systems classified as weakly nonlinear. Here, the nonlinear component acts as a slight deviation from a perfectly solvable linear system. In perturbation methods, we introduce parameter epsilon to express the solution as an infinite power series. Substituting this back creates a stack of solvable linear equations. However, this generates secular terms, mathematical artifacts growing towards infinity, violating the reality of a bounded limit cycle. While perturbation methods resolve the hierarchy of individual linear responses, this unbounded growth makes them incompatible with long-term periodic analysis. If a system's behavior will eventually settle into a steady-state periodic closed loop, we can approach the math from a different angle. Returning to the phase portraits of the van der Pol oscillator, this graph clearly displays a stable, continuous orbit. The trajectory repeats itself exactly. Applying Fourier's theorem, we express periodic motion as a sum of harmonic functions. Truncating to a single harmonic approximation, we substitute it into the nonlinearity. Discarding generated higher-order harmonics balances the equation, yielding a direct algebraic relationship between amplitude and excitation frequency. Balancing harmonics provides the exact parametric design equations engineers require to calibrate amplitude and frequency in vibration control mechanisms. Both perturbation and harmonic balance rely on a specific assumption. The system requires a dominant linear stiffness. If that stiffness drops to zero, the math fails. We see this strong nonlinearity during the violent snap-through buckling of a compressed structural beam, or in the bistable magnetic oscillators used for energy harvesting. For a pure cubic oscillator lacking linear stiffness, standard harmonic balance fails as amplitude increases. Instead, we use the elliptic balance method, employing Jacobian elliptic functions. Adjusting the modulus k warps the function's shape, locking perfectly onto the exact nonlinear dynamics. For systems driven by strong nonlinear physical forces, abandoning standard trigonometry for elliptic functions is the only method that retains true analytical accuracy. Extracting these approximate analytical solutions is a means to a physical end. This image plots the dense geometry of a chaotic attractor. It represents the intimidating reality of unregulated nonlinear dynamics. The amplitude-frequency equations derived from harmonic balance allow us to impose rigid mathematical order over this chaos. Engineers apply these specific equations in the ocean, tuning the negative stiffness of spar-type floating offshore wind turbines to mitigate destructive heave motions under heavy waves. Researchers use these exact same formulas to optimize the bifurcation dynamics of electromagnetic energy harvesters. Manipulating the bistable parameters broadens the device's operational bandwidth, allowing it to efficiently draw power from a wider spectrum of ambient vibrations. These methods translate abstract nonlinear phenomena into specific constraints for structural components. In the next module, we will plot frequency response curves to map where a system triggers jump resonance. Numerical integration shows us what a dynamic system is doing in the present. Approximate analytical solutions grant us the mathematical leverage to engineer exactly what it will do in the future.